my screen?
Yes.
Yes. Good. Okay, we can start. And today we will start to speak about general relativity. So in the previous lecture we considered Newtonian cosmology. So we considered the case of evolution of the volume, which involved in three-dimensional space. And we discovered, I just remind that we will have, in this case, three model of universe. This is closed, flat, and open. And as we also discovered that to understand which exactly model of the universe will realize, it's enough to estimate the mean density in the university and compare it with some critical value. So we found this, which depend only on Hubble constant. So in this case, they already said destiny is a density. So in the sense that the density will tell you how this volume will evolve, and in classical mechanics it means how the universe will evolve. We also discussed that this is not correct because we need to work we was working in classical mechanics in some volume which is involved in three-dimensional space, but for cosmology we need to consider the evolution of space. Why? And in principle, the differences between, now we will discuss general relativity, the differences between classical mechanics and, we can write here, then general relativity. Okay, so now we ideologically will consider why we need to use, instead of Newtonian mechanics, instead of Newtonian equation of gravitational field, we need to consider relativistic case. And after this, we will start to work with the formulation of general relativity, with object which we are using, because general relativity is more complicated than classical mechanics, because classical theory of gravity due to using tensor analysis. In general relativity, we will work and we will see that if, for example, in classical theory of the field of gravity, the space and time is different, so they are working, they can live without each other, I might say like this. Also, in principle, we just by definition consider that space is flat. In general relativity, we will see that the space can be curved, and in general case. Just a second, I need to answer very quickly. So, okay, we will start from formulation of what is the inertial mass and what's a gravitational mass. So, let's write. Okay, what is inertial mass? Inertial mass. So we can find the definition for the mass by two ways. One of these, this is inertial mass. And what is this? So let's call it M with index I, put it, for example, as a, here. And inertial mass, this is some proportional coefficient between force and acceleration due to the Newtonian law. So it means that inertial mass determine inertial properties of the body. So you are writing what I say. I will not write everything. So MI determine inertial properties of the body. Because it's understandable. So if we have the body with different mass, we need to apply the different force not to push this body, because this body has a property of inertia. From the other side, also the bodies has a property to create gravitational field. So, and this we can call gravitational mass. If we will consider it just in simple Newtonian mechanics, so we can write that the gravitational force, it doesn't important to put here a vector, I can write it in scalar form. So I can put the gravitational constant, of course, and two masses, M1, M2, divide on R squared. And in principle, I will put here the index G, just to recognize that mg, this is gravitational mass. So let's consider that. So this is like two properties of the body: inertial and gravitational. For example, if we will consider the gravitational forces which act on the some mass from the Earth, I will put here Earth, and for example, the Earth has the radius R. Let's put like a R without index, and the Earth has a mass M. We can write that it will be F G. Okay, I also put here also index to recognize that this is gravitational mass. Let's consider some simple task, some simple question. If the body has the mass has the inertial mass, so in this case, under acting of the gravitational field of the Earth, this body will have acceleration. So we will use the second Newtonian law. This is F divided on M I. Okay, and I will put here this expression for the force. So G M gravitational divided on R squared, M gravitational divided on M inertial. This is acceleration of free acceleration. Okay, we will put here G, and we have G M gravitational divided on M inertial. Very famous. So we obtain this, these relations. So, and as you know, well, maybe I hope that Galilei made experiments, and he finally discovered that the acceleration of all body near to the Earth's surface is the same. So it means that A equal G. But from this, we understand that in this case, we have this equality. So it means that inertial mass equal gravitational mass. For now, this equivalence between inertial and gravitational mass already estimated with a high accuracy. So it was made a lot of experiments. And so it means, and you can write as a conclusion, that even Galilei law, we can say like this, would say that all bodies, when they fallen down in the same gravitational field, they have the same acceleration. And this statement brings us to the principle of equivalence of inertial and gravitational mass. Okay, are you in time to write everything? Are you here?
Yeah, we're here and we're in time.
Okay. So just when you will show me your concept, it should be not only the same formula which I'm writing, but also some explanation. In principle, Einstein, you know, but I will not use the time to speak about special relativity theory. So you worked with this, I think, and special relativity theory working with the inertial reference system. Please write it. Special relativity works with inertial reference system. Inertial reference system, it means that the system move with a constant velocity, rectangular constant velocity. But Einstein started to ask questions the first, but why? And as a result, as we know, we have Lorentz transformation in special relativity. But the question was why the law of the nature are the same only in inertial reference system. Because in inertial reference, in special relativity, what is important? What is the main goal? So if you have some law of motion, for example, or nature, you can pass from one reference system to another reference system using some transformations. In special relativity, this is Lorentz transformation. So, and the law of nature or some principle should be the same. It will be strange if you have one law in one reference system, you move in another reference system, and something crucial changed. So it's really not a good description of the nature. And the question was, but why everything is working well only in inertial reference system in special relativity? And the idea of Einstein was also to join together not only inertial reference system, but also not inertial reference system. No inertial reference system. And just a second. So, and now we will consider what it means. So the first statement, which is idea to joint, and after this we will consider very famous Gedanken experiment. Gedanken, this is the same like thought experiment. It's an experiment when you sometimes in principle you can't use this experiment, you can't realize this experiment in reality, but logically you can understand something very important which can allow you to build the theory. So the idea was the same, because the problem that, for example, in special relativity, the law invariant to the Lorentz transformation. But if you will take the expression for the gravitational field in classical mechanics and apply Lorentz transformation, it will be not invariant to move from one reference system to another reference system. And this is the point. This is not a good. It means that something you need to change. Also, the additional idea was that to join together gravitational field or describe gravitational field as a non-inertial reference system. So the idea is that a non-inertial reference system, I will put like this reference system, we have the inertial forces, which is proportional to mass, inertial mass. From another side, in inertial reference system, we can have the gravitational forces, which is proportional and gravitational. So, and we can put it here, Fi, Fg. But since we have the equivalence principle, and we, from this principle before, just consider it Mi equal Mg, we can intuitively make the conclusion that the inertial forces, and you can write it as a conclusion, a short conclusion, that inertial forces equivalent to the gravitational forces. Inertial forces equivalent to gravitational forces. This is main idea when you can feel the smell of this, the idea of general relativity. And this Gedanken experiment, or thought experiment, very famous. It's sometimes called Einstein elevator. So in principle, it's been called Einstein elevator, which can demonstrate how this works. So let's put here, maybe, okay, I will try to, here, Einstein elevator, oops, elevator. So the example is the following. Let's consider that we have some elevator, closed elevator, which we hung, so it's fixed. And okay, we will put here poor person to make experiment. So, and we will consider that this elevator is located in some gravitational field with somebody want to, okay, sorry, I have some message, students maybe, okay, strange. I put okay, everybody can. Okay. So the gravitational field with a free acceleration, I will put like this. On this body, we apply, we understand that acting the gravitational force, mg. So, so this body feels the tension of the gravitational field because, for example, it can be in gravitational field of the Earth. Which is this reference system? This is inertial reference system. Inertial reference system. Okay. And we understand that inside of the elevator, we have just classical mechanics. And when we made experiment, we will cut this this fixed line. So in this case, the elevator will falling down, and we understand that of course this poor boy also will fall down. But we understand that he will be in the situation of weightlessness. So he will be like a, like an astronaut. But the second part, the second side of experiment, let's consider the same elevator. The same elevator, and let's consider this elevator far from the gravitational field. So we don't have any gravitational forces which acting on this elevator, like a spaceship, for example. But we again put here some. And but we are doing the same. We will push this elevator exactly with acceleration, which is equal free fall acceleration minus g. And this is already, this is a non-inertial reference system. Okay, non-inertial reference system. But the person who will be in this elevator, he will feel. So in principle, it will be, we can write, it will be inertial forces, and he will feel these forces, which equal, so if I will put the axis like this in direction of A, I can write MA, what will be MG. So if this person will be absolutely enclosed elevator, so without any windows, he will not recognize he is in a gravitational, this elevator is located in gravitational field of some planet on the Earth. All this elevator is moving. And this is main idea that we can't do any experiments to recognize if, of course, we don't see anything which is moving relative to us. We can recognize this is the forces of inertia, or this is gravitational force. So this is idea of this elevator. You also can write the equivalence principle of Einstein more precise. It means that all physical laws, we can say like this, in inertial and homogeneous accelerated elevator, will be the same as in English. Okay, we can say in the same as in a fixed elevator, which is located hung in homogeneous field or in homogeneous gravitational field. No, any experiments can't divide this homogeneous gravitational field from homogeneous field of inertial forces. What is also important and we of course need also to remark it, that in this case the tension should be the same. I mean, the tension of gravitational field the same as the forces of inertia. So this is the main idea. Okay, main idea, instead of gravitational field, we can consider a non-inertial reference system. Of course, you can. We need to remember that in any case, the inertial forces are different. Have a different, sometimes different behavior than the gravitational forces. Why? Because, for example, when we go to infinity, gravitational forces decrease to zero. But for inertial system, when we have, for example, rotation, we know that it will increase. So, this, of course, should be all time under control. This is also a point. Okay, now I also would like to do a retention and to an additional point. So we consider it a principle, everything. I also would like to mention that why the general relativity need to be built, why from the point of observational things. Everything was beautiful with Einstein with Newtonian theory of gravity, but and maybe I said before, the problem was with one of the planets. So the story is such a way that in 19th century, when the Newtonian theory of gravity was applying to looking for new planets, it was discovered Neptune, and Leverrier decided, not only Leverrier and others astronomers decided to also to apply it and to check the influence of, for example, of all planets on the motion of each of the planets of solar system. And the nearest planet to the sun, this is Mercury. And it was discovered that if you will consider, so if this is sun, so this is Mercury, and for example, others planet, if you will want to calculate very precise the orbit of the Mercury, for example, not obvious Mercury, you can use another planet, you need to take into account gravitational field of, in principle, all planets, because they also act on Mercury, on this planet. Totally, and they applying such a way that, in principle, the orbit of the Mercury should be like this. So we say about precession of the orbit. This is like such a kind of rosette orbit. This is Sun. Of course, I exaggerated this. It's not the orbit of Mercury is not so elliptical. We know that planets in solar system move on almost circular orbit, but the idea like this. and due to the gravitational field from another planets. And I don't remember correctly, but it's more than the influence of all planets make an effect such a way that we have a shift. We call it shift of the. Let's put it another right, like this and like this. So we have this shift of Mercury perihelion, which is more than like a 500 angular seconds per 100 years. So it's a very small value. From this, more than 500 is around 540. And everything can be explained, taking into account the gravitational field of the other planets, especially Jupiter, Mars, and like this. But the problem was with 43 seconds per 100 year. It's a very teeny, very small value, but it couldn't be explained in the framework of Newtonian classical mechanics. Usually, if you have in this dynamical problem such a kind of result, you can suggest that we have some additional planet, and it was suggestion that we have some planets between Mercury and the Sun. It was called Vulcanus, and this planet act on the Mercury such a way that additionally creates this 33 seconds per 100 years. But this planet finally it was discovered, but after this cancelled, so we don't have any planet between Sun and Mercury. And it was one of the problems why Newtonian theory doesn't work in this case. What is this? Also another question, when it was a question to Newton, what was gravity and how this gravity, transform from one point to another point, which is a mechanism which allow to feel Earth immediately the gravitational gravity of the Sun. And maybe you see, the Newton answer is that hypothesis, I don't want to invent any hypothesis. So in sense that I don't know. So this is work and it's good. But what is the idea of what is the gravity? I don't know. And it was also the second question, so we can put it. Second question, what is the gravity? So as a third point, again, I already said that this is the point why everything working well in special relativity inertial reference system, and we can't use non-inertial reference system. So this is the third point, which I already said before. Also, now we can feel how, and we will find principle from Gedanken experiment, from additionally solved experiment of Einstein. We will find the equation what is the gravity. So and we will see that the gravity, and you can write already the gravity is a curvature of space. And simply we can see it using Gedanken experiment, which call, I don't know how it's exactly to this name of this, but I will call this Einstein disk. Einstein rotating disk. By the way, I also want to say it. Of course, you also can make experiment like with elevator. Of course, not like this with elevator. It's dangerous. But experiment which you can feel all time when you are moving in train. So really, when you sit in train and train move with a constant velocity, and you will close your windows, you see everything okay. So, but when the accelerator for the train will move with acceleration, we start to feel that there is some force which pushed you to the seats. And if all windows are closed, you can't recognize. I can tell you that, look, now I have a special device and I switch on the gravitational field. And you will not prove me that, no, this is inertial forces. Of course, if you will open Windows and we will see that, the platform is moving, of course, we understand that this is motion. But if windows are closed, so we can't recognize this motion. This is more simple experiment with the train. Now Einstein disk. Okay. So let's consider some solid disk. Solid disk and with radius. Oops, sorry. With radius r, and the length of the circle L. So if we have no moving, no rotating disk, or for example, we consider from the point of, if the idea to measure from one side r radius and from another side L. And for this, we have some measuring ruler, some like a solid measuring ruler, which we used to measure it. Okay, so we put these rulers and we can calculate how many rulers we have, and we can calculate this distance, and also here. So let's, for example, we consider that it's not moving because it's not rotate, and we have observer on some distance which look on everything. From another side, if we will start to move this disk, and we will use ruler to measure, and this ruler move with the disk. So what we'll discover that since we have, and let's consider this rotation with the speed near to the speed of light. So we know that from Lorentz transformation, we know that we have that this ruler will become shorter, so it will be L0. So we have some ruler with, for example, L0. And if everything moving with, we can put some velocity where it will be 1 divide v square divide on c square. Okay, where c is the speed of light. So we will see that if we will measure, and we understand that Lorentz contraction is acting along the motion. This is important. So it means that if we will measure the distance, this radial distance, it will be the same as in the case of without motion. But if it will be rotate, so all time we can consider that V equal constant. But in any case, this is already non-inertial reference system, even with constant velocity, because this is not a straight motion. This is a curve motion. So, and this is not non-inertial reference system. Non-inertial reference system. Okay, in this case, we will have that our ruler, let's put it here, I don't know, like this, will be shorter. And if we will put measuring this L, this circle, if we will put shorter ruler due to this Lorentz construction, we will put much more rulers than in the case when we have inertial reference system. So what it means? It means that in this case, the ratio L divided on R will be not equal to pi. In Euclidean geometry, we of course understand that L equal to pi multiplied R. Okay, but we can see that if we apply special relativity, if we will take into account the Lorentz construction, if we will take into account this motion, so non-inertial reference system, we can see that the Euclidean rules doesn't work in such a case. It means that, and for this case, for example, this is more than 2 pi. It means that for the observers who are moving with acceleration, the rule of Euclidean geometry doesn't work. When we have such a kind of situation, when L divided on R doesn't equal to pi. So we have the example of this. This corresponds to the curve space. As an example, we can consider the example as a two-dimensional space, like a surface, because we not like a surface. Of course, we can't, for our brain, can't reconstruct the three-dimensional curve space, because we are by ourselves, we are living inside three-dimensional space, and of course all our sensitive things of our body, they are such ways to recognize everything inside three-dimensional space. Because sometimes we will do an analogy with two-dimensional space to the surface. So in two-dimensional space, we understand that the rules that L divided on R equal to pi when we have a flat surface. And okay, we can draw here circle. So, and really in this case, we have L divided on R equal to pi. Everything is okay from this point. But if, for example, we will have we will have surface with positive curvature, like a sphere, and if we will on this sphere we will draw the circle. So in this case we will have the different geometry. So in this case L divided on R not equal to pi, By the way, if we also put here triangle, so the sum of all angle equal 180, but in this case, we will have angle, we will have triangle. I can put it, for example, even here. And this, it will not correspond to the case as in the flat surface. So the sum of the angle will be more than 180. Okay, this is a sphere. This is flat. This is sphere. And there is also the surface. The third case, like this. The surface, I forgot this word. Saddle, okay, saddle. So the saddle surface, which using on the horse, you know. And this saddle surface, we have even much more different case, because in this case, the L divided on R will be more than 2 pi. And if we will draw here triangle will be like this. So the sum of the angle will be not equal 180. From the point of, there is such a kind of, and we will meet it in general relativity. In principle, this is, yes, it's okay in general relativity. So we can tell about curvature of the space. Even not in general relativity, but in geometry, we have such a kind of object, mathematical object, which we call curvature. For example, in geometry, we have Gaussian curvature, K, which call the letter K. And Gaussian curvature, in simple, it can be much more complicated, can be writing like a proportional to 1 divided on 2 main radii, R1, R2. So what it means, for example, for flat and this main radius, we need to put not from the circle, but you know, from the center of the curvature of the space. For example, for the flat case, we can see that R1 we can put equal R2 and then to infinity. And in this case, Gaussian curvature equals 0. So when we tell about flat space, we tell about 0 curvature in this case. For the sphere, if the center of the sphere here, okay, so this is, for example, radii. So, and this is R1, this is R2, which are the same. For the sphere, we have K, since R1 equal R2 equal R, we have proportional 1 divide R squared. For the saddle surface, we have this radii like this. So the point that I will clean it here. So that one radius, one part of the surface are created such a way that we have 2 different radii of the surface. One radii, this is from this side, and another from this side. So, and if we will choose some direction, okay, it means that this surface is organized in such a way that the surface, to make the surface with something, you need to put it between 2 radii. And this radii in opposite side of the surface. Why? In this case, we have k proportional minus, so you can see we have a minus here. R1, okay, I will put model here, R2, like this. We also will use such a value which we will call the sign of the curvature. This is k small, sign of curvature. So, and we can see that, and for us it will be just much more convenient to recognize immediately. So, for example, here we write that k equals 0, here k equal plus 1, here k equal minus 1. This is just an example of 3 possibilities of the space which has a I would like to mention that this space has a constant curvature. Such a kind of examples has a constant curvature, and 3 kinds of curvature: 0, positive, and negative. For example, this space with negative curvature, so called Lobachevsky space. And when Lobachevsky was working with such a kind of strange space with a negative curvature, there is a story that I read it some time ago, that his colleague couldn't understand why it's important, it's interesting. It's just some mathematical trick, nothing which could be applying to the real nature. Of course, Lobachevsky made many discoveries, very important in mathematics. And when he died, his colleagues, when they would like to mention really great results of Lobachevsky, they decided even not to speak about this discovery of space with a negative curvature, because it was like, it looks like strange. We will see that now this is crucial also in cosmology. So in principle, we can have a model with a negative curvature. Of course, not obviously we can have a space with constant curvature. We can have a space much more complicated, and in two-dimensional, and the example of two-dimensional surface, we will consider, for example, which much more simple torus. So such a kind of, okay, it should be the same. It's not beautiful. I will try to do it much more like this. Okay. Okay, this toroidal geometry, toroidal surface. So why it's so if when you will go to cafeteria and will order, for example, for donut, such a kind of sweet things, sweet cake, you need to remember that you eat 3 kinds of geometry, because in this case we can see that if we are working, we consider this part of the surface, okay, which is outside like this. So this part of the surface can be organized by 2 radii, this one and this one. So I will put R. But what is important that all these 2 radii are on one side of the surface, on this part of the surface. When we are inside, let's put a green here. In this case, this part of the surface should be organized by the 2 radii. One of these, again, this is R larger, R, this one. And the second one are small, which is, you can see in opposite side of the surface, then r big. And it means that we have the positive curvature. Sorry, I will put k small, plus 1 here, k equal minus 1 here, and in these 2 points, of course, at some point we need to have it, k equal 0. So this is representation of 2D surface, okay, two-dimensional surface. Of course, it can be applied for three-dimensional space like this. In advance, I can say that that by fortune, and you will see this miracle really. You will see that when we will work with a model of universe, you will see that by fortune we have for the universe the space with a constant curvature. This is, and you will see it from equation, from everything. So we will see is that this is a result of the property of the universe. Matter distribute homogeneous and isotropical. Why by fortune? Why we should be happy with this? Because, but you know, we can't exclude that geometry can be maybe much more complicated, which what we can understand for now. But why we should be happy with this? Because otherwise, if geometry of space in the universe could be much more complicated, like for example, this one with a curvature which depend on the angle, this angle. So in this case, the cosmology will be much more complicated now, and we could spend not 1 semester, maybe 4 semester to understand it. So that's just to remark. Which is conclusion? What conclusion you can write to fix? And the idea of this Gedanken experiment of Einstein disk, the conclusion such a way is that accelerating motion, you can write this conclusion, accelerating motion, which is equivalent to the gravitational field, bring us to idea of to the conclusion about curved space-time continuum. Curved space-time continuum. So this is main conclusion. Again, I didn't remark it, but okay, now I use space-time continuum. So I use these words because, and you already also know from special relativity, when we are working in relativistic theory, we know that space and time, in this case, together. Okay, so I will not spend time of course, we will write all the equation exactly for space-time continuum. In the lecture of Minkowski, it's about special relativity. It's 1908, if I remember correctly. He said very famous words that from this time, the space and time, which was considered separately and independent, now they are in a shadow, and only their connection together is independent. So the point that In classical mechanics, we can consider time separately and space separately, but in relativity, we already independent. We can consider only the space-time continuum. So, okay, if you have some question, you can ask for this part, because after this we can start already to formulate everything with equations, to start with the tensor analysis. Are you here?
Yeah, we have maybe questions.
No questions. Okay, because some you ask some question, react something. So because it's very difficult to give lectures and don't feel any feedback. You can ask questions in Ukrainian language, which language you prefer. Okay. If you don't have questions, now we can start to work with a mathematical formulation of general relativity. But in the first, as I already said, the general relativity is more complicated than classical mechanics, because the mathematical object which we will use, this is tensors. I think we already met with tensors. Did you work with tensors before?
Yes, sometimes.
Yeah, sometimes. So I think you worked in electrodynamics like this. So and the equation of gravity we will write in in tensor form. So it means that we need to in the first to understand the mathematics and notations. And we start with the co, write the title of the lectures, co and covariant, covariant and contravariant vectors, in parentheses tensors. Covariant and contravariant vectors or tensors. So in the first so covariant echo I will write like this. Okay, in the first we need to speak about Einstein summation. Einstein summation. So what it means? It will be very, in principle, it's very convenient. It was invented by Einstein, and you will see that it's really convenient to use. So the first, we can let's consider some scalar function. For example, phi. Okay, this is some scalar function, which is function of x, y, z. So this is some number in any point of the space. We will put a three-dimensional space. We can write a differential of this function, which, okay, this one plus, sorry. Okay, but to write all of this with much more comfortable form, I will do this one. I will call x like a coordinate with index 1, y with index 2. Sorry, I put it so. X with index 2 and z x3. Okay, in this case I will have that d phi equal, so d phi по dx1 dx1 plus d phi по dx2 dx2 plus d phi по dx3 dx3. The same I can write like a sum. So this is sum d phi by dx, and here I put n for dxn, and n from 1, so we have 1 to 3 to 3. In principle, understandable that we can generalize all of this for arbitrary dimension of space. I can put much more coordinate, why it's much more convenient. The summation of Einstein, it means that we will not write this sum, but we will just write d phi by dxn. So, but we will understand that if we have the index which repeat, so like this n is repeat 2 times. In this case, this is called summation index. Summation index. Summation or also dummy. It means that index in Russian, in Ukrainian language, we can tell we use non-speaking немой index. So because you will see why it's called like this. Also, but it can be different situation when, for example, we have some function. Let's consider it. I will move here. For example, we can consider some function f. It can be also the function of 3 x1 x2 x3, okay, 3 coordinates. And for example, we consider this function in one reference system. Let's consider it in reference system X. Behavior this function in this reference system, okay. So, and I go to another reference system. Let's call it Xi. And this function will be some function, okay, schematically I will write like this. So, and we want to understand how it will be changed due to go from another reference system, from one reference system to another reference system. So Xi, the new reference system, Xi1, Xi2, Xi3. So what, for example, we can consider the derivation of df by dxn. In this case, we will have, since we need to use this function in this reference system, we need to write df divide on dx m, just, you know, by the rule of to obtain the derivation, but dxm on dxn. So this I wrote in the Einstein notation because it means that when we write like this, it means, and you can see, for example, here, which is a summation index here, m. Here, m is summation index. But n on the right side, we can see it only once. So n doesn't have any pair here. And n, in this case, we call free index. Free index. Free index in Russian or in the Ukrainian language, we call it говорящий. So it tells us how many, principle in this case, it tells us how many equations we will have. For example, I can put here the f, if this one expression inside this one expression, it means that we have correspondingly 3 equations. df by dx1 equal df by dxm, dxm, dx1. It means, so, and we need to rewrite, you know, to open this m. It will be also df by dx2. Understandable, yes, the same, but it will be only dx2, and the same for df for dx3. So the free index tell us how many, in this case, equations we will have, expression we will have. What about m index? We when we can see that m has a pair, so together with additional index, we understand. So this is a summation index that we have here the sum df by dxm, dxm, dx1, m from 1 to 3. Okay, so it means that this is df by dx1, dx1, but dx1 plus df for dx2, dx2 for dx1 plus etc. So now you can see how it's convenient to use Einstein notation, because instead to write all this number of the things, it's enough just to write this one formula. So we already need to finish, and I will finish on this point. In the next lecture, we will consider, we will formulate a new object. We will find a new object which we will call covariant and contravariant vectors with a generalization to tensors. So if you have some question, please ask. Now I will make a screenshot. Okay, no questions.
Maybe not.
Okay, in this case, we can meet on Monday.
On Monday. Okay. Yes. Yes.
On Monday, yes. Okay. What is interesting? In Italian the same, but in Italian language, relativity it's la relatività. Try to pronounce it. It's very complicated to pronounce it because with article la, it's became much more complicated in English language. Okay, this is just a joke. Good day for you and good weekends.
Thanks. Thanks for watching.
Thanks for you.
Goodbye.